Professor Loeb reports that his numbers indicate 3 Atlas has been shedding mass at an extreme rate, possibly blasting apart into many smaller bodies. New computations from Harvard's Avi Loeb point to a catastrophic breakup during solar passage, with 3I Atlas fragmenting into perhaps millions of pieces. We're looking at a shattered object whose parts are being pried apart by the sun's tides. The physics is measurable, the math exact, the implications immense. And yet, as dramatic as that natural scenario sounds, it may be the more straightforward answer. Because there's another path, one Loeb has outlined with equal rigor. And the observation window to learn which story is true is closing fast. Here's the unanticipated constraint. Energy budgeting demands a nucleus at least 14.3 kilometers across to sustain the mass loss rates 3I Atlas showed. Carbon dioxide sublimation requires a radiating surface consistent with a body about 20 kilometers in diameter, far larger than estimates for the true core of 3I Atlas. But Hubble imagery from July 2025, about 3 weeks after discovery, capped the diameter near 1 to 2 kilometers. That's a 16-fold gap. You can't hide 14 kilometers of ice and rock from Hubble's optics. The next point runs counter to standard comet behavior in every solar system catalog. The object was getting bluer. Comets heated by the sun typically appear yellow-white as dust scatters light toward longer wavelengths. 3 Atlas shifted into the blue on approach, hinting at metallic compounds reflecting in ways a normal icy nucleus does not. This morning, we got word the object brightened more than expected, and its color is blue, bluer than the sun. That's startling, since dust should make it red. Picture a snowball turning glossier and more metallic the nearer it moves to a flame. That's not how known natural processes work. The textbook mechanism is outgassing, volatile ices sublimating under solar heat, jets providing reaction thrust. From early August to the October 29 perihelion, sublimation climbed from roughly 330 kilograms per second to about 2 million kilograms per second, a jump of nearly 6,000 times. Daily mass loss rose from sub-million ton rates to roughly 2 million tons per second at peak.
But here's where the energy balance breaks the conventional model. Solar flux at perihelion delivered about 700 joules per square meter per second to 3I Atlas. Loeb's estimates show that driving enough CO2 and H2O sublimation to match the observed loss would require at least 617 square miles of absorbing area, equivalent to a 14.3 kilometer sphere. To extract that much mass from ice, we need a huge surface. And it turns out that implies an object on the order of 20 kilometers across, far beyond the original size estimate. For a natural comet, that points to breakup into many pieces, so the combined area of all fragments reaches the required total. Yet Hubble's July constraint fixed the core at 1 to 2 kilometers. Only one physical route reconciles the thermodynamics: catastrophic disintegration into millions of smaller fragments, each contributing its own exposed surface. Together, the thermal cross-section can meet the energy demand. The math drives this conclusion.
On November 9, 2025, 11 days after perihelion, British Astronomical Association observers Michael Butner and Frank Nebling obtained images that changed the investigation. Instead of a diffuse debris fog typical of thermal breakup, they recorded organized collimated jet structures. An antitail extended about 950,000 kilometers toward the sun, defying standard solar wind dynamics that push material away. The main outflow stretched roughly 2.85 million kilometers anti-solar, nearing twice the Earth-Sun distance. Additional frames resolved at least 7 distinct jets with geometric order, precise directions inconsistent with chaotic explosive fragmentation. Most viewers will miss what that geometry implies. But if you follow the numbers, you're seeing something without precedent. Thermal stress debris fields should look random. These jets showed coherence, more like channeled flows than passive venting.
Loeb estimated that maintaining on the order of 50 billion tons per month in mass loss would either require large intact nuclei, undercutting the fragmentation story, or innumerable fragments somehow keeping exceptional outgassing capacity. Natural physics struggles to satisfy both constraints at the same time, which leads to Loeb's controversial alternative. If standard cometary outgassing doesn't parsimoniously fit the evidence, the patterned jets, the vast sustained loss from myriad small shards, the geometry, then technological propulsion belongs in the hypothesis set. Advanced systems can produce exhaust speeds far above sublimation, needing much less propellant to yield the observed accelerations. Directional thruster arrays would produce exactly the kind of collimated, geometrically ordered jets seen in November. The observations, as Loeb states plainly, will choose between models. He isn't claiming proof of artificial origin, he's posing competing hypotheses with equal discipline, allowing that fragmentation is viable while insisting the data decide. Hubble's November spectra and Webb's December imaging will either show debris fields that seal a natural breakup or reveal structural anomalies that force a fresh interpretation.
Then the trajectory results stopped mission planners cold. 3I Atlas was accelerating beyond what solar gravity alone allows. Near closest approach, it gained on the order of 94 kilometers per day squared, already exceeding 150,000 miles per hour and still speeding up. In celestial mechanics, forces don't appear from nowhere. This traveler entered detection on July 1, 2025, found by Chile's Atlas survey, the third confirmed interstellar arrival after Oumuamua in 2017 and 2I Borisov in 2019. 3 sightings in 8 years suggest such visitors may be more common than we thought. By late August, Webb's infrared suite resolved a CO2 envelope around 348,000 kilometers across, approaching the Moon's orbital distance from Earth. Yet the spectra were odd. Iron to nickel ratios diverged from standard comet mixes. The molecular fingerprint felt off, like a passport with valid stamps in the wrong order. Stack that against earlier interstellar cases. Oumuamua showed no sublimation, an inert tumbler through the inner system. 2I Borisov was textbook, steady outgassing, gradual heat-driven breakup in line with models. 3I Atlas sits in an impossible middle, clearly cometary in makeup, yet presenting accelerations, mass loss behavior, and jet architecture unmatched in known natural populations. Here's the next 40 days. 3 Atlas flies closest to Earth on December 19, 2025. Hubble and Webb are running intensive spectroscopic campaigns through late November and December. This is humanity's lone chance at high-resolution scrutiny. Once it slips beyond practical limits, the window closes for good. The 6 weeks of observations become the permanent record, no do-overs. By January 2026, detections fade. In spring, it will pass beyond Jupiter's orbit, accelerating toward deep space. Every spectrum, every orbit fit, every resolved image gathered now will define what we know about 3I Atlas. Watch the schedule. Miss this window, and we may never learn whether we witnessed remarkable natural fragmentation or encountered something the interstellar medium contains that our physics doesn't yet anticipate. Born around another star, this body may have drifted for eons, arriving just as Earth possesses instruments to study it. The coincidence is astonishing. Now, as it crosses our neighborhood, it's either demonstrating a natural phenomenon so extraordinary science must stretch to include it, or revealing that interstellar space harbors objects we never foresaw. Either way, the stakes are profound, and time is short. Observations in these final weeks will decide whether the millions of fragments are ordinary debris dispersing under orbital dynamics or pieces of something far stranger. The breakup is real, photographed, measured, quantified. The jets are real, logged by multiple independent observatories. The extra acceleration defied pure gravity. The trajectory deviations are computed with care. Whatever processes produce these signatures will define not only what 3I Atlas is, but what stories the void between stars has been carrying. The scopes are locked on, data streams are growing, and somewhere in the spectra, in the trajectory fits, in the thermal budgets, lies the answer to whether countless shards of ice and rock are obeying familiar physics, or whether something unprecedented just passed through our solar system at the first moment in human history when we were capable of recognizing it.